Okay, so you guys tell me then real quick. Let's just look at these three planes, the blue plane, green plane, the orange plane. What would you call the blue plane then? The XY plane. That's it, right? It's the XY plane. Okay, more importantly, what's the equation of the XY plane? Z equals 0, right? Does that make sense? Because the only thing that has to be true in the XY plane is that Z has to be 0. X and Y could take on any values. Agreed? Okay, so the equation Z equals 0. What's the green plane called? The YZ plane, yeah. What's its equation? X equals 0. And the orange plane? The XZ plane. And its equation? Y equals 0. Okay, and if we wanted to plot an ordered triple, because now when we're talking about a three-dimensional space, we need more than just an ordered pair. We need 3 coordinates, right? Because we have 3 dimensions in our universe here, in our space. And so what if we wanted to do something like this, right? If we wanted to plot the point 2, 3, 4, then what's that mean? Well, that means starting at the origin, which is now the intersection of all 3 axes, not just 2. We're going to tell the ant to move 2 in the x direction, positive 3 in the y direction, and then positive 4 into the z direction. And so it's that point right there in space that I'd be graphing, not on a plane. Okay. All right, so let's try this. Let's just try, and this is not easy to do, to graph these things in a way. I mean, because we're trying to draw on a 2-dimensional surface. It's hard to draw 3-dimensional things on a 2-dimensional surface, but we'll give it a try. What if we want to graph the line x plus y plus z equals 1? And maybe we'll take some tricks from what we did previously, where instead of trying to isolate a variable, we're just maybe trying to find intercepts and things like that. Okay. So any ideas how we could do this? Okay. Yeah. So how about if we start off? Why don't we maybe, like, if we're trying to graph a plane, what would the intersection of this plane that we're going to attempt to graph here, the intersection of that plane with another plane, like the XY plane, what would that look like? Okay, yeah, intersections of planes typically are going to be lines, aren't they? Right, where 2 planes intersect, they're going to intersect at a line. So let's maybe start off by just setting z equal to 0, and let's graph the line that we get in the XY plane. Okay, so x plus y equals 1. Now, if we're trying to graph that, well, we know how to graph that. We would just find the x-intercept and the y-intercept. So the x-intercept would be where y is also equal to 0. And what's that give us? 1. Okay. So we get a point in the xy plane. We get a point at, I'm going to go by, just so this thing's a little bit bigger. Let's say that, like, we're going to graph this thing by 1/4. Wouldn't that be nice? Yeah. Just get a hologram? Sure, why not? Okay, so we'll say that there's one, there's one, there's one, and there's one. How about? Okay. So we get a point in the xy plane. We get a point at the x-intercept is going to be at 1. The y-intercept would also be at 1, right? And so in the xy plane, I'm just going to graph a segment here. We get that segment in the xy plane, right? Okay, how about in the, let's look at maybe the xz plane, the flat tabletop plane here. So that's going to be the one where now we're going to set in the xz plane, we're going to set y equal to 0, and now we just get the line x plus z equals 1. Well, wouldn't you agree the intercepts are going to be on the x-axis at 1 and the z-axis at 1, right? And so we end up with this line in the xz plane. And then by doing the same thing in the yz plane, we would just be setting x equal to 0, and now we get the line y plus z equals 1, and its intercepts would be at 1 and 1 on the z-axis and the y-axis, right? And so we create, darn, I keep doing that. We create something like that. Okay, how does that help us? Well, now you got to use your imagination here. But if we connected those 3 segments and created a plane out of that, right? Would you agree that the plane we're creating looks kind of like, yeah, it looks kind of like this, right? I mean, it's going to be tilted at an angle, but it's going to look like that triangle, right? Yeah, so right, so it's kind of cutting. If this is the tabletop, it's cutting up through the tabletop at an angle, right? And then like this y-axis is just like vertically sticking out of the table. It's gonna cut through that at an angle. This is a little better picture, maybe something like that, right? You get the idea? And that's just one little piece of that infinite plane, but we just graphed a triangular piece so it's easy to visualize, but it goes forever, right? Okay. Give me thumbs on that. Is that making sense? Sort of, kind of, maybe? Okay. I mean, it's hard to visualize. Okay, so now next step is we want to represent systems, linear systems, right? So this is going to be, we just determined that each of these linear equations in 3 variables represents a plane. So a system is going to include 3 planes, and the solutions of the system, just like in a 2x2 linear system, solutions are every ordered triple in this case that satisfies all 3 linear equations at the same time. So it's going to be all the points that simultaneously lie in all 3 planes, right? That's what a solution to a 3x3 system would actually mean graphically, right? So let's explore that a little bit.